Let's let c be our minimum value of this function. So we have that f of x is greater than or equal to c. Multiplying our function by x turns this into a polynomial. And so when x is positive, we have that the polynomial on the left-hand side is greater than or equal to c times x. So let's graph y equals c times x. It's going to be a line that passes through the origin. And somewhere here, where x is positive, we're going to have this polynomial that's tangent to this line at 2 points. Let's subtract c times x from our polynomial. When we do that and graph, we'll have another polynomial that's tangent to the x-axis at 2 points. We'll call those points a and b. If we let g of x be this polynomial, we can see by inspection that the degree of g is 4. So these two roots can be written either as x minus a squared times x minus b squared. We can eliminate this option because if we have an odd power of these two factors, then instead of being tangent to the x-axis, it's going to intersect. So let's write it as the square of x minus a times x minus b. This is the square of a quadratic. So let's replace this inner part with a quadratic with a leading coefficient of 1 and it's squared. And we'll expand the square of this. I want to use v-etas to find k. This coefficient has the most promise because it only has one variable. So let's find the coefficient of x cubed from g of x on the left-hand side. We find the coefficient of x cubed by multiplying 3 of these x's and one other factor. So we'll have a minus k, a minus 98, minus 72 and minus 18 times x cubed. And this simplifies to the negative of k plus 188. So we'll set these two coefficients equal to each other and solve for k. We'll try to solve for m now by using convenient values of x. So for example, if x is 18, these factors disappear and we're left with minus 18c. And on the right-hand side, 18 squared minus 18m plus n squared. And we'll do the same with these other values of x. We'll number these equations 1, 2, and 3. We can get rid of the c variable by dividing these equations pairwise. So if we take equation 2 and divide it by equation 1, equation 2 is minus 72c on the left-hand side, and we'll divide by minus 18c on the left-hand side. This left-hand side cancels to 4, and then we have on the right-hand side the square of this fraction. Taking the square root of both sides, we have that the fraction is plus or minus 2, and we'll multiply by the denominator. We'll repeat this process by dividing equation 3 and equation 1. So on the left-hand side, we'll have 98c divided by minus 18c, and then this fraction on the right-hand side. Canceling the left-hand side, we have 49 over 9, and we'll set that equal to the square of this fraction. We'll take the square root of both sides again, so the fraction is equal to 7 over 3, plus or minus, and we'll multiply by the denominators. So now we have two pairs of equations. Let's number these over again 1 through 4. So now we're going to say that equation 1 comes from this first one, where this is equal to plus 2 times the expression on the right. And equation 2 will be minus 2. And equations 3 and 4 are going to come from here. After combining like terms and simplifying, we end up with this much nicer equation. And we'll repeat this process for all 4 of these. Recalling that each of these pairs of equations come from the same plus or minus situation that we have here. We can't have equations 1 and 2 be true at the same time, and similarly we can't have equations 3 and 4 be true at the same time. So we're going to test the situations where equations 1 and 3 are true, 1 and 4, 2 and 3, or 2 and 4. And we'll call these cases 1, 2, 3, and 4. We'll start with equations 1 and 3 are simultaneously true. I'll rewrite them here. We'll solve both of these for n and set them equal to each other. Solving for m, we end up with m is equal to 350. The problem statement has that these conditions are true when x is positive, so we'll check for both solutions x greater than 0. In a quadratic, if our solutions for x are a and b, then our quadratic can be written as the product of these two factors and expanding. We can test to see which of these are positive or negative. If one of them is negative, then their product is negative, which is the constant term of this quadratic. Recall that g of x is the square of this quadratic. So we want to test whether n is positive. So we'll take our value of m here and plug it back into this equation and solve for n. Here n ends up being negative, which means one of our solutions for x is negative. So this is invalid and we have to exclude this. So let's check out case 2. Here we're going to simultaneously have equations 1 and 4, and I'll reproduce them here. This time we can add both equations, and I'll factor out the 42 and solve for m. We'll plug this back into our first equation and solve for n. This is positive, so we have a valid solution. So let's find our formula for k. Here it is, and we'll plug in our value of m, which gives us 8. This is our first valid value of k. We'll go on to case 3. Case 3 has equations 2 and 3. Again, we'll add these two equations. We have 78 times m on the left-hand side, and I'll factor out a 6 from the right-hand side. And solving for m, we get 110. Let's check our value of n by plugging into the first equation, and this is positive. So now we'll solve for k. This gives us 32, our second value of k. And we'll go to case 4. That's equations 2 and 4. We'll solve both of these equations for n and set them equal to each other. And solving for m, we get 194. Plugging back in to solve for n, this is also positive, so our solutions in x are also positive. So we'll solve for k. This gives us 200, our third value of k. The problem asks for the sum of all the valid values of k. That was 8, 32, and 200, and our answer is 240. If you'd like me to solve any other math contest problems, please leave them in the comments.